Welcome back. I am super thrilled to have you here for another explainer. Today, we're taking a fascinating journey to look right under the hood of digital logic. We're going to explore the invisible architecture that actually allows us to communicate with our machines. It's a world of pure logic, zeros and ones, and honestly, it's absolutely brilliant. All right, think about this for a second. When you press a key on your keyboard, how does your computer instantly know which one it was among dozens of options? You got letters, numbers, symbols, shift keys, the whole shebang. Yet the response on your screen is just instantaneous. What you're actually triggering is a massive, lightning-fast translation problem happening right at your fingertips. And today, we're going to crack exactly how that translation works. Okay, let's dive into this. Here is our step-by-step roadmap for today. We'll start with the language of computers, then move into decoders translating to states, encoders compressing information, the mathematics of logic, and finally, actually building the digital circuit. Let's get to it. Section 1. The language of computers and those foundational alphabets. So, digital systems basically rely on 5 core coding schemes. We've got natural binary, binary coded decimal, or BCD, gray code, octal, which is base 8, and hexadecimal, base 16. Now, what's incredibly clever here is gray code. Notice that note about how only one digit changes at a time? Unlike standard binary, where multiple bits might flip all at once when you count up, gray code is designed specifically so that transitioning to the next state only ever flips a single digit. It's a brilliant engineering trick used to drastically reduce errors in physical switches and communication lines. Moving right along to Section 2, decoders, translating to states. At their core, decoders are basically addressing devices. They convert information from one number system to another. Mathematically, what they're doing is taking a small handful of inputs, let's call that n, and expanding them out into 2 to the power of n possible states. So if you have 2 input lines, a decoder can address 4 different output states. 3 inputs, you get 8 states. It literally takes compressed data and fans it out into specific, actionable addresses within the computer. Now, taking all that abstract math and turning it into physical reality is where things get really fascinating. Tracing the flow from the input bus on the left, running right through those internal logic gates, it illuminates exactly what's happening. Depending on the engineer's choice, this construction uses either NAND gates or OR gates to achieve the exact same propositional logic. It's quite literally truth algebra wired into physical existence. And hidden right in those circuit notes is a fantastic little detail. If an engineer decides to swap out a component and use a NOR logic gate in this design instead, it entirely flips the output logic into an active high-state logic. By just changing that one specific type of gate, the entire behavioral paradigm of the device is completely inverted. It just goes to show how precise and delicate digital engineering really is. All right, Section 3, encoders, compressing information. Time for the reverse function. These two are perfect opposites. While decoders expand n inputs into 2 to the power of n states, encoders provide the exact reverse functionality. They gobble up a huge number of inputs and compress them down into a highly efficient n-bit binary code that corresponds to the state of those inputs. Which brings us right back to our keyboard question from the beginning. This is solved by a specific type of device called a priority encoder, and this concept is absolutely crucial. In a priority encoder, inputs are arranged in a strict hierarchy from lowest to highest priority. Why does that matter? Well, imagine you accidentally mash 2 keys on your keyboard at the exact same millisecond. The priority encoder instantly looks at both active inputs, completely ignores the lower one, and solely encodes the highest priority input. It's kind of like a built-in traffic cop for digital signals.
That takes us to Section 4, the mathematics of logic, and how we actually calculate that priority.
Okay, looking at the propositional logic for an 8 to 3-bit binary encoder. Yeah, it seems really dense. But engineers use foundational rules, things like De Morgan's laws and the exclusive or XOR logic identities, to wrangle all this complexity. These distributive properties let them take massive, messy equations and simplify them into clean, repeatable patterns that can actually be manufactured. And finally, Section 5, building the digital circuit, taking it from math to machine. This brilliantly illustrates the final hardware blueprint. Every single symbol here is dictated by the math we just looked at. You've got your input bus on the left, feeding into the processing bus made up of AND gates, which then feeds directly into the output bus utilizing OR gates. Oh, and that line at the top over the EN, that represents an active low enable switch, basically turning the whole system on or off.
The number 8 here is totally the star of the show. We're looking at a configuration taking exactly 8 separate inputs, say 8 different buttons on a keypad, and flawlessly compressing them down to just 3 output channels labeled A, B, and C. It is just incredibly efficient.
But, engineers always want to be more efficient. So instead of building a massive, sprawling circuit board with individual NOT, and OR gates scattered everywhere, modern engineering lets us bake that math directly into a single, highly customized multi-input XOR integrated circuit. It does exactly the same job, but takes up a fraction of the physical space. It's a real game changer. So the real takeaway here is captured perfectly in this quote from the source notes. Quote, "If more than one input becomes active, the input with the highest priority will be encoded, while the states of the other lower priority inputs will be ignored." These circuits are absolutely ruthless. They're designed to instantly filter out the noise, making sure a clean, unambiguous binary code gets sent straight to your computer's processor. It really makes you appreciate the invisible world right beneath our fingertips, doesn't it? Which leaves us with a pretty fascinating thought to end on today. If these basic microscopic logic gates are working at lightning speed to instantly filter out the physical noise of our clumsy keystrokes, what other invisible digital noise is your computer silently managing, translating, and prioritizing right now while you watch this explainer? Thank you so much for joining me to look under the hood today, and keep questioning how your digital world is built.